Okay, so this is just kind of an introduction to how to collect data using the Revolutions of the Moon lab for my astronomy students. Okay, the first thing to start is just to log in. And this will bring up the kind of opening screen here. You just go to File and then Run. The thing should pop up for the date. You don't have to change that at all. Just hit OK. And what it'll show is kind of a wide view of Jupiter. So in this case, we're going to be tracking one moon and figure out the mass of Jupiter. Now the idea is we know how gravity works. It works the same for all bodies. So if you're able to look at the orbital period of a moon around a planet or a planet around a star, you can figure out the mass of the central body. Because the stronger the gravity is of that body, the faster the orbiting body will be. Now here, this is kind of what a view you'd get if you look through a telescope. You'd see kind of Jupiter, probably not as well in terms of bands here, but through kind of a small telescope, you're able to see a large disk for Jupiter, and then four dots that are Jupiter's four largest moons. Now, since we kind of have an edge-on view of Jupiter, it doesn't, the moons, we don't see kind of the entire circular motion. We kind of see the planets move back and forth. See if I click it here. See how they seem to kind of move left to right. So the trick here is to kind of figure out which moon is which, and then measure its position as it moves back and forth and catch its entire period. Now it's a little hard here, but what we can do is kind of cheat a little bit and apply certain parameters. And if you go to File, select Features, we can put ID colors. And now each one is his own color. So this one here, this blue one, it's Ganymede. Callisto, yellow. Europa is white. And red is Io. So for us, we're going to go ahead and pick Ganymede here. Which is actually the largest moon in the solar system, and kind of the one that has the third largest orbital period. So once you click on a moon here, this little green arrow clicks, and what you can do is just record it to the computer. Yep. Try it again, and if it'll show up, it should have the lettering. The name and then the kind of number there if you're correctly on the moon. Okay, so this thing right here allows me to record. If you're recording all the moons, you click on each moon to record it to the system. But we're only going to do Ganymede here. Okay, and the terminology they're using here is as if you were measuring through a telescope. It'd be kind of hard to kind of objectively make a measurement. So what they are doing is kind of using Jupiter's diameter itself as kind of a way to measure. So right there, it's about a little under 5.5 Jupiter diameter away from the center of Jupiter. And since we're going to call this side west, this side east, we'll just let it go. So if you hit next, as we can see, Ganymede has moved a little bit. I'm going to put it on there and record. And the idea is to go around enough times such that you get at least one orbital period. Now, of course, occasionally a moon might be directly behind Jupiter, so in that case, it'd be kind of hard to record it. You can either put a 0 there or just record it's being basically blocked or eclipsed by Jupiter itself, and just go on to the next step. Now, I didn't really need to do so for this case, but it does allow you to actually zoom in. That's what these other buttons here pretty much got a full set of data for Ganymede. But if you needed to get a little closer up, you can hit 200, 300, 400, and that'll allow you to kind of get a closer up view. That's only if you needed to. But I have enough points, so I'm going to go ahead and try running it for Ganymede. So we go to File, Data, then Analyze. This brings up a new window here called Jupiter Satellite Orbit Analysis. Now the next step is go to Data, select your moon. Since I only have data for Ganymede, that's the only highlighted option. So what I have here is I have a nice set of data points here. They're kind of moving, and the way it's plotted it out, it's time using units of Julian date. But each tick mark is a day in this case. And then my vertical axis here is going from kind of the center point of Jupiter there, east and west in terms of kind of distance. They mark it as a positive and negative. So going back and forth, it creates this kind of sinusoidal pattern. So what I'm going to do is try to fit a curve that will give me a period and an amplitude that matches these data points, and then from that I can then use Kepler's modified version of Kepler's third law using that period and amplitude to find the mass of Jupiter. So next step is plot, okay, and fit sine curve. Alright, so in this case I got to put in some generic values to start off my curve. So in this case my 0 point here is 866. The period there. So in this case, how many points? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to say 7.5 to start off, and then I'll try correcting it from that. And then the amplitude, that's from the 0 point up to the peak. So this case, this is around 8. So I'm going to start with that. Okay, here's my curve. Doesn't quite match yet. So what the next step is, there's 3 slider bars that allow me to go back and forth to try to fit this curve. Okay, and how to do that is there's one slider that just moves the whole curve itself horizontally, one curve that stretches it, that changes the period, and then one, it stretches it horizontally, and then there's also a stretch or shrink vertically, and that's for the amplitude. And the idea is kind of this RMS residual here that it's kind of tracking the error between your curve and the data points. And you want to try to get that as low as possible. And it's red if your most recent correction changes that to cause it to be a larger error, and then green if it's making it smaller. So if it turns green, that means you're going in the right direction. If you ever have to go too far, say if I move here and I'm not able to go any further, I can correct for that by just hitting this kind of circular arrow. That just recenters the slider bar, so I can do it further. There's also another tool here, and that adjusts kind of the amount of how much each slider motion changes. Coarse is large changes, fine is smaller. So let's go ahead and try to get some data for this. Okay, so that's going to be kind of the smallest I'm going to be able to do with this set of measurements. So it's pretty good. Um, so in this case, the things you want to record. Here is for the period. Is this second number here? So that's your period. Your amplitude, you want to make that 7.4335 here. So that's your second number. And from that, what you'll need to do is the next step of converting them from units of days to years and Jupiter diameters to Jupiter diameters to AU, because that's how Kepler's law is designed. So in that case, your lab handout will show kind of how to do that, but for the most part, there's 365 days in a year. Okay, so if we put those calculations in, just show you an example. And then for to convert AU, it's 1 AU is about a little over 1,050. So we'll put that in. So as we can see, our values are very small in the units we have to use. Just make that 0. So then the next step, to find mass, in that case, that's equal to this ratio of A cubed divided by the period squared. So at least for these examples, I get something that's a little under 1,000th of a solar mass. And again, you should expect that's something small because, again, this with the equation, it's in terms of ratio of the sun. So this one's a little smaller than expected, but still a fairly good calculation. So go ahead and try it yourself and see how well you can do.